This video is about the integrated rate laws. We've already seen about differential rate laws, and we can determine what the rate law is by looking at initial rates and how changing the initial concentration can change the initial rate, and then use that to derive a rate law. But we can also do this another way, and that is by just tracking how concentration changes over time, and there are some characteristics that allow us to determine what the rate law is. So our goal is to find the order of a reaction by just looking at concentration versus time data. So in other words, if you have a way of tracking the concentration of a reactant over time, like spectrophotometry might be an option, or even weight or volume of a gas, something like that, then you can figure out the rate law from that. And then we want to be able to use that to kind of in reverse predict the concentration based on the amount of time that's elapsed once we know the rate law. So to develop this, there are two ways of thinking about rate. One is for a reaction, this is like a simple generic reaction of A becoming B. The differential rate law, or just the ordinary rate law, is rate is equal to K times concentration of A raised to the n power. But another way of thinking about rate is by thinking about it as the slope of that line. So at some moment, the rate could also be thought of as minus dA dt. So that means we could set these two equal to each other, because both of them express the rate, and then use that to find the integrated rate law. Now, if you have had calculus or are taking calculus and you want to know the details of how this works, it's pretty interesting. I would recommend that you watch this video that's going to be recommended here. If you don't know about calculus, then I'm going to just show you the result of doing the calculus. So there's going to be three different cases. One of them is if n equals 0, so if this is a 0th order reaction, then the result is that we have a graph of concentration versus time that's going to have a negative slope, and it's going to be linear. The slope of this line turns out to be the negative of the rate constant, and the vertical intercept for this line is the starting concentration, of course, because that's the concentration at time 0. So if you're going to build the equation of this line, it's going to be concentration of A, that's the vertical axis, is equal to negative KT, remember K is the rate constant, plus the vertical intercept, which is concentration of A at time 0. So that is the equation that you get from this integration if it's a 0th order reaction. Now, a useful consequence of this is that if we have a way of tracking concentration over time and we find out that we get this straight line, then that means we know that the reaction is 0th order. What if n equals 1? And again, take a look at the calculus video that's going to be tagged here if you have had calculus and you want to know where this comes from. If not, this is the result of doing this integration. The natural log of concentration of A versus time will be a straight line. Again, the slope is the opposite of the rate constant, and here the vertical intercept is the natural log of the starting concentration. So to build an equation from this, the natural log of the concentration is equal to minus KT plus the natural log of the starting concentration. Once again, we can use this information kind of in reverse. If you have a way of tracking concentration versus time, and you find out that the natural log of concentration versus time is linear, then that means that reaction was a first order reaction. If n equals 2, again, look at the calculus if you know how to understand that. Again, look at the calculus if you know how to understand that. Otherwise, here's the consequence. In this situation, it turns out that 1 over the concentration of A versus time is a straight line, and this has a positive slope. That slope is the rate constant, and of course 1 over the starting concentration is the vertical intercept. So once again, building an equation of a line, 1 over concentration of A is equal to KT plus 1 over the starting concentration of A. And just like with the previous two, there's a consequence of this for doing investigations. If you track concentration versus time and you find out that 1 over A versus time is linear, then that means the reaction you were tracking is a second order reaction. It's an important quantity, now that we know about how concentration and time are related, called half-life. And half-life is just simply what is the time that it takes for half of a reactant to have been reacted. Let's take a look at what the half-life would be under the three different cases that we've investigated so far. If n equals 0, we know that this is the equation that relates concentration to time. So if we try to figure out what half-life is from this, we could say that at whatever time the half-life is, the concentration is going to be half of the original concentration. That's equal to negative k times t 1/2, because this is a specific time we're talking about, the half-life, plus the starting concentration. So if we subtract the starting concentration from both sides, we get starting concentration over 2 minus starting concentration is negative k times t. If we multiply both sides by negative 1, that means starting concentration minus half of starting concentration is k times t 1/2. That's the half-life. So that means that starting concentration divided by 2 is k times the half-life. So that means that the half-life is going to be the starting concentration divided by 2 times k. So a consequence of this is that because starting concentration is in the numerator, the bigger the starting concentration at the beginning of your half-life, the longer the half-life is. Let's take a look at this visually. Here I have in Desmos a graph of just a straight line with a negative slope. So this could be representative of our graph of concentration versus time. If we look at the length of the half-life from 10 down to 5, that would be cutting the concentration in half. That's how long the half-life is. From 5 down to 2.5 goes from the blue line to the green line. That is the half-life during that change. The next half-life is even shorter. The next half-life, even shorter, and so on. So as we go through time, the starting concentration at the beginning of that half-life is going to decrease. So that means the size of the half-life decreases as well. Now let's take a look at first order. If n equals 1, this is the equation that governs how concentration is related to time. So that means that the natural log of the starting concentration over 2 would be the concentration at half-life equals negative k times the half-life plus the natural log of the starting concentration. So that would mean that the natural log of the starting concentration over 2 minus the natural log of the starting concentration is equal to minus k times the half-life. So that would mean that the natural log of the starting concentration minus the natural log of the starting concentration over 2 is positive k times the half-life. We can rewrite this using the laws of logarithms as natural log of concentration of A at the start divided by concentration of A at time at half-life equals k times half-life. So the A naughts are going to cancel out, and that leaves us with 1 over 1 over 2, which is 2. So that means the natural log of 2 is equal to k times the half-life. So if we solve for the half-life, it's the natural log of 2 divided by k. And since the concentration does not appear in this equation at all, the half-life does not depend on the starting concentration. Let's take a look at this visually as well. Now I have a graph of what the concentration versus time graph would look like for a first order reaction. Let's look at the half-lives. As it drops from 10 down to 5, that's the half-life. As it drops from 5 down to 2.5, that's how long the half-life is. As it drops from 2.5 down to 1.25, that's the length of the half-life. As it drops from 1.25 to 5/8, there's the half-life. So we can see that no matter what the starting concentration was at the beginning of the half-life is still the same length every time. What about when n equals 2? This is the equation that governs how time and concentration are related to each other. So at the half-life, the concentration would be starting concentration divided by 2. So 1 over A naught divided by 2 is that concentration on the left-hand side of the equation. That's equal to K times the half-life, T1 half, plus 1 over the starting concentration. So that means 1 over the starting concentration over 2 minus 1 over the starting concentration is K times the half-life. So that means that 2 over the starting concentration minus 1 over the starting concentration is K times the half-life. 2 minus 1 is 1, so that means 1 over the starting concentration is K times the half-life. So if we divide both sides by K, we find out that the half-life is equal to 1 over K times the starting concentration. So since the starting concentration is in the denominator, this means as time goes on and the starting concentration at each subsequent half-life is smaller than it was before, that's going to make the half-life get larger and larger. Here's a graph that would simulate what a second-order reaction would look like if it's concentration versus time. Let's look at the first half-life. As we drop from 10 down to 5, that's the length of the half-life. From 5 down to 2.5, the half-life's a little longer. From 2.5 down to 1.25, the half-life is growing. From 1.25 down to 5/8, it's growing even more. And then the next half-life, we can see it's growing even more. So the half-life's continually getting longer and longer when it's a second-order reaction as time goes on. One last topic is working with multiple reactants. So we saw how to do concentration versus time for a single reactant and then derive the rate laws using the integrated rate law technique. But what if we have more than one reactant? If that was the case, then rate will be equal to some rate constant times the first reactant raised to some order times the second reactant's concentration raised to some other order. So if we have two reactants, the rate law is going to depend on both of them. Rate is equal to K times A raised to the N, let's say, and times B, the other reactant, raised to the M. So how we can deal with this is we can make one of the reactants have a concentration that's so much bigger than the other reactant that it essentially stays constant throughout the entire reaction. So let's take a look at this. Let's say we have 0.01 moles of A and we have 10 moles of B at the beginning of a reaction. They're one-to-one stoichiometry, so we're going to lose 0.01 moles of A, but we're also going to lose 0.01 moles of B. And we'll gain 0.01 moles of C, but we don't really care too much about that. Afterwards, there's no A left. Its concentration has gone to 0. B, well, it still has 9.99 moles left, basically the same amount that you started with. So during this entire change, B is essentially a constant. So we can take these two constants and put them together and just make them a constant for that run. So what we'll do then is we'll track the concentration of A and use that to find what we call a pseudo rate law for a specific starting B concentration. So the rate is equal to this pseudo rate constant, KPS, times the concentration of A raised to the N power. So we'll find the order in A, and then we'll have this pseudo rate constant that we can get. It'll be the slope of the line or the negative of the slope of the line. What's the pseudo rate constant? Well, it's the constant that we made from the starting concentration of B and the real K. So it's K times the starting concentration of B for run 1. And that's raised to the M power, but it doesn't matter because it's a constant. Then we do another run. We just change the concentration of B, but still keep it way, way bigger than the concentration of A. Now we get a different pseudo rate constant, and this pseudo rate constant is equal to the real rate constant times the starting concentration of B. Now we'll have two equations. We'll have the old one, Kps1 equals K times the starting concentration of B for run 1 raised to the m power, and we have two unknowns, K and M. So we can use those two equations to find our two unknowns. Okay, here's an example. Here are two different trials where NO reacts with O3. And what we're going to do is, in one trial, we're going to make the O3 concentration 1 times 10 to the 14th molecules per cubic centimeter, which is way bigger. It's 1,000,000 times bigger than the actual concentration of NO, which is around 10 to the 8th-ish as time goes on. And then in the second run, we're going to double the concentration of O3, so we have a significantly different concentration, but it's still way bigger than the concentration of NO. And then we'll step through this and figure out what the rate law is. I'm going to switch over to graphical analysis to do this because it's much easier to visualize. Okay, in graphical analysis, I have the first experiment. This is the one where the concentration of O3 is 1 times 10 to the 14th molecules per cubic centimeter. And I put the time data and the concentration data for NO. And you can see the plot here. It doesn't look linear. Let's just test it to be sure. Put a curve fit in here. In fact, the R value isn't good, and once the line is on there, it becomes pretty obvious that there's a curve to this. So let's see if it's first order. We can do that by adding a calculated column here. And that calculated column, we're going to make that natural log of concentration of NO. And if you take the natural log of something, it doesn't have a unit anymore. Stick this expression in here. This is what we want. We want to take the natural log of something. So 1 times the natural log of NO, that's exactly what we want. So we'll click that. And it changed the value on the vertical axis to the natural log of NO concentration. Let's do a curve fit. And in fact, we get a very good R value and slope. So the M here is 0.001802, so that is the negative of the pseudo rate constant. So the pseudo rate constant is 0.001802. Okay, let's keep that in mind. I also put the second data set in here, and it automatically calculated the natural log of that as well. So let's turn that data set on. And when we do that, we find that we get a very good R value and a different slope. The slope is 0.0036, essentially. So now let's make use of this information to figure out what the rate law is for this reaction. So what we're trying to build here is that a rate is equal to K times concentration of NO times concentration of O3. NO is raised to some exponent. O3 is raised to some other exponent. And we're trying to do this by a pseudo rate constant. So for the first trial, we had rate was equal to the pseudo rate constant for trial 1 times concentration of NO, where Kps1 was equal to the actual rate constant times the starting concentration of O3, which was 1 times 10 to the 14th. And I'm going to leave the unit off here, but it was molecules per cubic centimeter. And that's raised to the m power. And then from the second experiment, we found rate is equal to Kps2 times concentration of NO. Again, we know that that's raised to the 1 power. And Kps2 is K times the concentration of 2.0 times 10 to the 14th molecules per cubic centimeter raised to the m power, because that was the starting concentration of O3 in the second trial. And then from the graph, we found that Kps1 was equal to the slope, which was 0.0018 per second, and that Kps2 from that slope was equal to 0.0036 per second. So from the definition of Kps2, we can know that K is equal to Kps2 divided by the concentration, 2 times 10 to the 14th. And that's going to be raised to the m power. So then we can substitute that back in, And that means that KPS1 is equal to K, which we're going to substitute in KPS2 over 2 times 10 to the 14th times 1 times 10 to the 14th. That's raised to the m power, and this was also raised to the m power. Rearrange. KPS1, first of all, was 0.0018. KPS2 was 0.0036. And 1.10 times 10 to the 14th over 2.0 times 10 to the 14th, both raised to the m power, is going to give us 1/2 equals 1/2 to the m. So m equals 1. So that means that this is first order in O3. Then we can substitute back in to find the actual value of the rate constant. So let's use that. K is equal to KPS2. Remember that was 0.0036. Let's put the units back in here. This is per second. And the original concentration was 2 times 10 to the 14th. And this is raised to the 1 power. And this is molecules per cubic centimeter. So K ends up being 1.8 times 10 to the -7th molecules per cubic centimeter second. So it's kind of a convoluted process, but that's how you can find the rate law when you have more than one reactant using the integrated rate law idea.